Alright, so my research project was done this summer during the Polymath Junior research project, looking at special knots and knot theory. So to define what's a mathematical knot, you can think of it as a string with zero thickness, and you loop it in some way in R3, and then you glue the ends together. Formally, it's an embedding of S1 in R3. It means it lives in R3 without self-intersecting. And we can define the simplest knot, which is the unknot, as just like an unknotted circle. This one you see here on the left. And knots live in 3 space or R3, but we can kind of use what's called a knot projection. So we project the knots from 3 dimensions down to 2, and whenever we have pieces that overlap, we record that as a knot crossing, just to record which piece goes above and below. So here are some projections of knots. This is the unknot, like I said before. This is the trefoil knot and the figure 8 knot. And an important study of knot theory is to distinguish between 2 knots. And we are allowed to think of them as being like a stretchy rubbery substance where we can move them around continuously without self-intersecting. And whenever we have knot projections where you can move one into the other, we consider them to be equivalent. And to go into a little more detail about these moves, we can do what's called Reidemeister moves, which is just like local moves you do in space. And whenever 2 knots are equivalent, there exists a sequence of Reidemeister moves to move from one to the other. An important area of study in knot theory is knot invariants, which help us distinguish between 2 knots. Some examples of these are the crossing number, the cross-cap number, determinant, tricalability, like the Alexander polynomial. And knot invariants are just characteristics of knots that are shared between all equivalent kind of knots. So whenever 2 knots have different characteristics of a certain knot invariant, then they must be different knots. An example of this is just a tricoloring of the trefoil knot right here. And a useful property of knots, which we will use, is looking at the surfaces that knots bound, and there are infinitely many of them. An example is the trefoil knot, right here in this example. On the left, it bounds a Mobius band, which has 3 half twists, which is a non-orientable surface. On the right side, it bounds a torus with 1 boundary component. That just means it's like punctured with, it's a torus minus a disk. It's 1 puncture. And we will look at orientable surfaces and look at the genus G surfaces, which is just the number of holes of a surface. So for example, right here we have a sphere with 0 holes as genus 0, a torus with 1 hole says genus 1, and then an n-genus surface. And we define what is the genus of a knot, which is the minimum genus of any surface that it bounds. An example of this is we look at the unknot, so it bounds a disk, and we kind of morph it into a bowl, and then we glue a disk. So whenever we glue, we're allowed to glue disks on the surfaces that they bound. This won't change the genus of the surface they bound, so we glue a disk on top of this and get a sphere, and sphere is genus 0, and we can't go below 0, so therefore the unknot is genus 0. And we define what's called a ribbon disk, which is just a disk that's immersed specially in R3. And whenever a knot bounds a ribbon disk, we call it a ribbon knot. And we can denote RD whenever D is a ribbon disk as the number of self-intersections of this ribbon disk. So for example, right here, here's a ribbon disk of the square knot. It has 2 self-intersections, so therefore it has ribbon number 2. And we define the ribbon number of a knot just to be the minimum ribbon number of all the disks that it bounds. And we looked at 12 crossing ribbon knots. So 12 crossing knots are just knots that have 12 crossings in their knot projection. And for a knot to be a 12 crossing, that means that no matter how you have a projection of it, you can't go below 12 crossings. And so we use some heavy machinery to find some upper and lower bounds of ribbon numbers of these knots. An example is a theorem by Meyer and Zupin. Whenever we have a knot K in R3, we have the ribbon number of it wherever, it just means that K adjoins k inverse, where the inverse is you just record the crossings of k and you just invert them, and joining them means you like cut off a piece of the knot and you glue it together with another knot. And it has an upper bound of the crossing number of k minus 1. And in addition, if it emits a symmetric union presentation with partial diagram D, the upper bound will now be the crossing number of the partial diagram minus 1. And a symmetric union presentation is just, you get like a diagram D, and you adjoin it to the inverse of it, and you're allowed to, by doing this, you'll kind of form like a little axis of symmetry, like this example right here. So you'll get your knot and you connect it to the inverse, and it'll form an extra axis of symmetry, and you're kind of allowed to like change like the tangles on the symmetry. It doesn't really matter, but we're concerned about the number of crossings on the partial diagram. So for this example, for the knot 12A 183, this partial diagram has 6 crossings, and the theorem states that it's it's the number of crossings minus 1. So therefore, it must have upper bound of 5. And again, look at a lemma by Meyer and Zupin, where when k is a ribbon knot, then has an upper bound of the genus of the knot. To summarize how we found this, we resolved all ribbon intersections of a ribbon disk through a special method, which is the cell door construction. Just whenever you have a piece of the ribbon disk that the ribbon knot is bounding and there's a self-intersection, you can do what's called a cell door construction. So you cut along like a little box right here, and you open the flaps up and then connect it to the bands here in a specific way that will result in a pointable surface. And it's doing this is called like resolving the ribbon intersection by using this construction, and which results in this surface having a genus R, or the genus of the surface, to be upper bounded by the ribbon number. And we can use this to compute the chromatic number, the Euler characteristic of the surface, which is the vertices minus the edges plus the faces. And we use that we could also use that to find the genus of a surface whenever we know the number B of boundary components. And another important theorem we use to find some bounds is the theorem by Meyer-Zupin again, where whenever we have a knot K having the ribbon number be equal to n, we can represent the Alexander polynomial of it as f of t times f of t inverse, whenever f of t has degree n, and the absolute value of each coefficient ai has an upper bound if n choose I, where I ranges from 0 to n. An example of this is the knot 12A 1202, where you can kind of represent it as f of t times f of t inverse, and we get that the absolute value of A3 is greater than 4, and it's greater than absolute value of A4 is greater than 1, which would result in a contradiction if the ribbon number was 4. So therefore, we must have at least a lower bound of 5. And we define the determinant of a knot, which is another invariant, and it's just the opposite value of the Alexander polynomial evaluated at -1. And we have a theorem where whenever we have a k as a ribbon knot, the determinant has an upper bound of 2 to the ribbon number minus 1 squared. An example of this is looking at the knot 12A 221. It has determinant 169, but if we assume that a knot has ribbon number 3, then its determinant must have an upper bound of 49. So therefore, we get that the ribbon number is at least 4. And now this leads into defining a special set like R4, which we use to find lower bounds of ribbon numbers. So I'm going to get to that in a couple slides. But to explain that, we need to construct a kind of combinatorial aspect of ribbon knots. So we define what's called a ribbon code. So we basically translate from a ribbon knot to a ribbon code in such a way where first we look at the ribbon disk that it bounds and convert it to a disk band presentation. So you'll have your ribbon disks, and then the bands will like go through them and intersect them. And this is like a similar presentation to what we saw earlier of showing an example of an immersed disk. And we record information, so we label our disks and our bands, and whenever we have an intersection going through our disk, like D2, we'll label that we'll convert to a graph where the vertices are the bands and the edges are vertices are the disks and the edges are the bands between these disks. And whenever a band goes between it and inside it, we label like the number. There's like it's positive and negative for just the orientation of the way that the band goes through the disks. And many ribbon disks that correspond to a lot of ribbon codes, the same with ribbon knots. So we can use this and variants of ribbon disks, and using the Alexander polynomial, which will come up in the next slide, to calculate the Alexander polynomial of a ribbon code, and it's useful for determining the ribbon number of our knots. So we define what's called Rn, which is the set of all Alexander polynomials for any ribbon knots with ribbon number at most n. An example of this is looking at R3. So we look at the Alexander polynomials of knots with ribbon number at most 3. And so you see like here 1 is just the unknots, the trivial vertex, and you have other examples here of tree graphs. And you'll notice that they all have 3, like most of them will have 3 markings on these edges. Some will have 2. And this was found before this project, but then R4 hasn't been created yet, so that's what, the main focus of our research project, and potentially determining R5. And so how we ended up finding R4 was we determined all ribbon codes with exactly 4 markings, and we calculated the Alexander polynomials of all these codes, and then we used these polynomials to improve the lower bounds of these ribbon knots. So we just write out all our tree diagrams with 4 markings, and we consider all the possible combinations we can use, so a little more combinatorial problem, and then we check for reducibility and redundancy, because you can do these up to symmetries like rotational and kind of moving around in 3 space. And we haven't found all the possible ways to reduce them, because we'll get some ribbon codes that have the same Alexander polynomial. However, this will be solved because we'll eventually create a program to compute the Alexander polynomials when inputted a ribbon code. Okay, so an example of reducing them is moving a band through them. I'm just going to skip through this because we don't have much time left, but these are just some examples of how you're reducing them and the thought process through it. And you can do it by hand, but we ended up using Sage to automate this and found 56 unique Alexander polynomials in R4, which is once again the Alexander polynomials with ribbon number at most 4. We also have codes to create the maximal list of ribbon codes, so we can kind of extend this to R5. And if the way we can find the lower bound is if the Alexander polynomial knot is not in R4, then it means it has ribbon number at least 5, so it must be in either R5 or greater. And we ended up looking at heterogeneous ribbon numbers, which I won't go into detail, but we use this to help find lower bounds dependent on the Alexander polynomial, and then capital C of K, which is the cross-cup number. And we were interested in finding jumps with the genus G ribbon numbers, which is what we defined here. I'm just going to breeze through that because we don't have enough time, but we ended up finding construction. We ended up finding a knot 12A 1202, where we have a jump between R1 and R0 because the difference is greater than 1. So yeah, to summarize, we found 56 ribbon numbers using our upper and lower bounds. We computed R4. We found lower bounds for highest genus ribbon numbers, and in the future we can kind of look at other 12 crossing knots and try to extend it to R5 and R6. A big thanks to Polymath Jr. and mentors Alex Zubin, Jeffrey Meyer, and Evan Scott for the guidance support, and groups RIB and all the co-authors. Thank you.